Hey guys, we're going to do more U substitution today, but the difference today is our integrals are going to be definite integrals. So we aren't going to do the plus C on these because I have actual numbers to sub in, okay? So, really everything's going to be done pretty much the same. We're still going to pick a U, we're still going to find du, we're still going to change this to an expression in terms of U. The only thing is, you have to be careful of, when you do math and you show your work, every new line that you create is supposed to be an equivalent expression of the line above it. Like when you've got an equation and you, in your head, you add 2 to both sides and you do a rewrite. That's an equivalent expression or equivalent equation to the one you have above it. So each new thing you do, you have to say, this is an equivalent, this is equivalent, this is equivalent, and then I have my answer. As much as you would like to say it's a thing, you know it's not a thing. When your work is incorrect and yet you get the correct answer, if your teacher catches it, they're not going to give you full credit. Wrong work, right answer, because you had expressions or you had equations in here that weren't equivalent to the ones above it. Your answer wasn't equivalent to what was above it. Okay? So, we have to make sure that everything along the way that we do is legal and an equivalent expression, all while changing this to an easier integral to work out. So, here we go. I'm still going to pick a U, so I'm going to grab my blue pen. I think this is messy, so I'm going to let U equal 2x plus 1. Let's see, the derivative of that is 2. Yeah, I can deal with that. So du is going to be 2dx. And I'm going to do a rewrite. I'm not replacing anything yet. I'm just color coding everything. 2x plus 1 is going to be blue. Everything left over is going to be red. You can see how this is going to turn into a U. I want this to turn into a du, but it's not quite ready yet. I want this to be able to match this. So you can see the only thing that's missing is a 2. Get you a 2 there. 2, keep it legal. Now, I'm ready to change this whole integral that was originally in terms of x. I'm ready to change everything to u's. I'm switching variables. You know why? My x expressions were way more complicated than my u expressions are going to be. So I'm making this easier by switching everything to a u. Here's what's going to happen. 1/2 the blue becomes a u. This whole orange cloud right here becomes du. Time out. There is something terribly wrong with what I just wrote. So, let me think about this. By now, you know that basically what this represents is the area under this curve from x equals 0 to x equals 4. These are x's. These are x's. This is an x. Look what's wrong with this. These are x's. This is u. This is u. They don't match. This is completely illegal. This is not an equivalent expression to the one above it. You know why? These daggone numbers right there. They don't match. You can't put everything in terms of u except for those and just leave them as x's. You also can't say, I'll deal with them later. Let me just go ahead and finish out my problem, then I'll change it back to x's, and then I'll put my x's back in. No. You've just changed this problem from a definite integral to an indefinite integral. So what on earth can you do that is legal? You can change your 0 and your 4. You can change the x values to u values. How do you do that? You use the relationship that you established in the first place. You said, I'm going to let u equal 2 times every x plus 1. So, I'm going to come over here. When x is 4, u is 2 times 4 plus 1. When x is 0, u is 2 times 0 plus 1. Okay? A little bit of extra work, not too bad, but now my x, when x was 0, u is 1. When x is 4, u is 9. This is completely legal. I changed this to u, I changed this to du. These are now u's. Now we may finish out our problem. Okay, now something else I want to note, I want to point out. Yesterday, you were evaluating indefinite integrals. Your answer was going to be an expression with an x in it. It's an actual function with an x in it. That was your answer. Not today. Today, your answer isn't a function. You all know what the answer to an indefinite integral looks like. It's a value. All you need out of this is a number. So here's the cool thing. Once you've switched from complicated x's to simple u's, don't look back. Don't recomplicate things by plugging an x back in it. Take what you got and run with it and get to your answer that way. So here we go. I've got 1/2 1 to 9 u to the 1/2 du. I'm going to get some space. I'm going to go 1/2. I'm going to raise it. Yep, raise it and divide. And I'm going to evaluate that from 1 to 9. So let's see, those cancel. I've got 1/3 u to the 3/2 evaluated from 1 to 9. So I've got 1/3 times 9 to the 3/2 minus 1/3 times 1 to the 3/2. This isn't hard. 9 to the 3/2. Well, remember, this means root. And we want to root before we cube. We don't want to cube and then try to square root some terribly large number. So here I go. Ready? Square root 3. 3 cubed is 27. So this part becomes 27. 27 times 1/3 is 9. And then 1, 1, 1, 1/3. There you go. So, again, I don't want to complicate things. I don't want to change this back to x ever. Remember, x is more complicated. X is 2x plus 1. There's more math involved. Don't give yourselves extra opportunities to make a mistake. So keep the simple version. Keep the simple version. You've got new numbers to work with. Just see it on through until you get your answer. Okay, this one, this is weird. That's not supposed to be up there. There we go. We're not going to have 2 dx isn't a problem. That was a typo. So I see this messiness buried inside something being squared. So I'm going to go u is equal to 3 minus 5x. du is going to be negative 5 dx. See if I can do a rewrite here. I'm not changing anything. I'm just color coding it. 1 over 3 minus 5x squared. Okay, so that's all there. Oh, and all that's left is dx. Okay. Just turn that blue. Everything's the same, everything's the same, everything's the same. So you know this is going to be a u. We've got to work with those. I want this to become du, but look, it doesn't quite match right now. So it's missing a negative 5. So let's get us a negative 5 out there. Balance it out in the front. Right, everything is still in terms of x. As we go to change it, let's work on changing our 1 and our 2. So when x equals 1, when x equals 1, u is 3 minus 5 times 1. When x equals 2, u is 3 minus 5 times 2. Go. Okay, new numbers. Sub in from 1, turn that into a negative 2, and from 2, turn that into a negative 7. This seems backwards to you, but this is the way it's supposed to be, okay? You plugged in the correct substitutions. You subbed in the correct u values for x values. Don't do anything weird. I mean, I guess if you wanted to, you could swap them and make that not a negative anymore, but whatever. Okay, 1 over u squared. And then all of this becomes du. You might feel better writing this as this so that you can do an antiderivative on it. I'm going to raise it and divide. Do you like that better? I made my u to the negative 1. I just did that to it. You might like that better. So negative 1/5 times negative 1 over negative 7 minus holy moly, that is a lot of negatives. Jeez. So remember, it's when you're doing an antiderivative, you go antiderivative like big F of B minus big F of A. So This is the number that you always sub in first, and then it's always a minus, and this is the number that you sub in second, okay? So, negative, negative, negative. Negative 1/35, 1, 2, 3, 4, plus 1/10. Ooh. $14. How did I know that? Because I know that, what do I know? I know that 5 times 12 is 60. That was one that I knew really well. So 60, 65, 70. All right, next one. This one's a little bit of a challenge. If you let u be 1 over x, then du is equal to negative 1 over x squared, and that's not going to work. So let your u be the other thing in the problem, which is the natural log. So natural log of x du, there we go, 1 over x dx. Rewrite and just color code it. 1 to e. I think I'm going to slide my fraction apart. So I've got ln x over 1 times 1 over x dx. Okay? So I just took this fraction and I slid it apart. Slid it, natural log of x stays on the bottom, 1 over x dx. Now, oh nice, look, perfect, perfect. They match. So this is going to become du, this is going to become u, these need to become u's. Alrighty, well, when x is equal to e, u is equal to ln of e, which is 1. Ha, that's nice. When x is equal to 1, u is ln of 1, which is 0. Sorry, can you all see what I'm doing? There we go. Making some replacements. 1 turns into 0. E turns into 1. Ln x turns into just u. And oh wow, all of this matches, so it becomes du. Shoot, that's nice. That one probably looked the scariest of all, and it was the one that involved the least amount of work. All right, that just about wraps it up for definite integrals involving u substitution. Let me just say that I've spent several summers in AP workshops listening to people who have been AP graders for years. I also got the opportunity to be an AP grader this summer. I can tell you, if you have a definite integral that involves u substitution and it is in the free response part of your AP exam, so not on a multiple choice where they don't look at your work, but if it's a free response and they're going to look at the steps involved, they'll say something like, you get a point for picking the right U. You get 2 points for your new integral, right? 2 points for your new integral, making sure that everything is in terms of U, and then 2 points for the right answer. If you don't turn everything into U's, you're going to lose some of those middle points on the way to your answer. That's the way the rubric is set up. You're going to get a point for doing this right. You're going to get a point for doing this right. You're going to get a point for doing this right. If you don't show that you've done all that, you're going to lose points. So they're really picky. I'm going to be really picky. I'm going to be picky on your test. If you don't change those, you will not get all the points possible. Okay, flip your paper over to the back. This is kind of cool. This is going to save you some time. That's always a good thing, saving you some time. So I want to talk about even and odd functions. I could go over the whole theorems up there, but I'm not going to. Let me just make up a super easy even function. Y equals x squared is kind of the most basic even function. What if we're looking from here to here? So let's look at y equals x squared from two numbers that are opposites of each other. It's like -5 to +5. What if I had you do an integral like that? What if I had you integrate x squared, an even function, from -a to +a? Well, remember dx. Remember what this means. This just means, hey, find the area under the curve of x squared from here to here. So if you're looking at the area under the curve, you would be looking at all of this and all of this. Well, if the function's even, that means the graph has perfect y-axis symmetry. So you know what you could do. Instead of doing this integral, you could do this integral. Right? You could just find this area and then double it. Why? Why would you want to do that? Because you all know that in many integrals, when you're evaluating a definite integral and you do an antiderivative on this, a lot of times when this second number that you're subbing in is 0, so easy. This can be, sometimes, most of the time, this can be a much easier integral to do than this one. Okay? And I'm not even going to take the time to, let me do a rewrite. I know this is an even function, x to the 6th, it's even function, and it's moved up 1. So I can say that this is going to be totally equal to twice here to here. And I could take the time to evaluate it. And if you do, blah, 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 you get 284 over 7. Okay? It is easier if that's a 0 than if that's a 2. Okay, that's if your function is even. What if your function is odd? Let me show you a most basic odd function. The most basic odd function is y equals x cubed. Let's say that I wanted you to look at the area under the curve. Look at the area under the curve from a negative number to its opposite of x cubed, an odd function, dx. Okay, this is a terrible drawing, but it's supposed to have it's supposed to have origin symmetry. So what we'd be doing is let's look at the area between the function and the x-axis from here to here. So that would be all of this and all of this. They're supposed to look the same. If I could draw, they would look the same. So, but here, you know what's going to happen. I'm not calling this a negative area. There's no such thing as a negative area. But when this is a result of an integral, you know that the result of your integral, just for this portion, will be a negative value. The result of this portion, as a result of the integral, will be a positive value. They're going to be the same. So your integral is going to take this area, it's going to throw a negative on it. It's going to take this area and throw a positive on it, and it's going to add them together, and what are you going to get? You're going to get 0. So here, this looks complicated, but tangent is an odd function. If you picture your little whoosh on tangents, you know, and then this is an even function. So overall, this is an odd function. And the area under the curve from -1 to 1 for an odd function is 0. Okay, so sometimes you're able to identify, hey, this is an even function. Sometimes you're looking at a picture of a graph of something, and you're like, oh, well, I can just double it, you know, because they're, you know, symmetric. It's got y-axis symmetry. I can just double it. So anyway, keep those in mind as you're evaluating integrals because they can be nice time savers.